The plan today is to go over how to relate. That's what you see, right? Okay, yeah. Existence and uniqueness of solutions of AX equals B to what we learned in class. So we will be using the pro tip and the semi-pro tip to find these solutions, just so we can make it more concrete into the kind of methods that we want to be using. So let's talk about existence of solutions. When you say that a solution for a system of equations AX equals B exists, then what you mean is, and what you want to show, is that B is a linear combination of the columns of A. If you can show that B is a linear combination of the columns of A, you can say that the system of equations has a solution. There may be a unique solution, there may be infinitely many solutions, you don't know, but it does indeed have a solution. Now, if you remember, by definition, we know how to show if things are linear combinations of each other. Let me get my pencil here. One way to do that is by definition, where we write down something like B is alpha 1, E1 column plus alpha 2, second column of A2, and so on. So this is the same as this. And another way is what we want to use by using the semi-pro tip. So what is the semi-pro tip? What does it do? It simply lets us count the number of linearly independent columns in any matrix A. That is the objective of using our semi-pro tip. How we will use it into getting our solutions is we're going to use it to get somehow a relation between the linear combination of A and the fact that that we can find the number of linearly independent columns given a matrix. So if I give you a matrix A and I say, show if B is a linear combination of columns of A, what you will do is, if you were using the semi-pro tip, you'd want to say that this is equivalent to saying that U and UE, when you formulate this equation in the standard form, have the same number of linearly independent columns. Now, this doesn't seem like it translates from what we've been doing, right? So how do we say that these are comparable? How do we say that these two lines imply this one? So one way to look at it is we, in a previous proof in our class, we proved that the number of linearly independent columns in A transpose A is the same as the number of linearly independent columns in U. So number of independent columns in A transpose A is the same as the number of independent columns in its LU factorization. So if we know that, what we can say is, I'm going to make a matrix A transpose A which will have an LU decomposition given by LU. And I'll make another matrix where I'll add B as a column of A. So it's A1. So then my AE, and we need more space here, but my AE essentially becomes, that's first column of A, second column of A, to an mth column of A, and finally the vector B. So if I know that the number of linearly independent columns in this set, let's demarcate that. Number of linearly independent columns in this set is, say, K, then the number of linearly independent columns in this set, if this is equal to K, then I can say that there were no new linearly independent columns added to AE than they were in A, right? But if I find that that was not the case and there was K plus 1 linearly independent columns in AE than they were in A, then B is not a linear combination of the columns of A. Is that clear? So when I say that, so let's say I have this set of vectors, right? This is your A matrix, the one in pink. It's all the columns of A listed together. So we can say that's the A matrix. Yeah? And using this formulation, it's LU decomposition, I found out that there are K linearly independent columns in A. How do we do that? We take A transpose A and we look at the columns of U using the semi-protip. Do you remember the semi-protip? You can look it up. It's very easy. So the semi-protip is not this. Let me enlarge this. This is a semi-protip. What does it do? It counts the number of columns, the number of linearly independent columns given a matrix A. Right? This is in our book. And we're wanting to count it. So this function gets a matrix A, and what it will do is returns the number of linearly independent columns, which is different from our protip, and we'll discuss how. So what does it say? It says that when you do LU factorization of your A matrix, when you do LU factorization of your A matrix, you get a P, an L, and a U. If we define K to be the number of linearly independent columns of U, which is also the number of linearly independent columns in A, which we know empirically, we can say that K is equal to the number of columns of A, which is K is equal to M, if U has no zero diagonal elements. What if, so that is when I have U of the structure where none of the elements on its diagonal are zeros. So I can say, okay, so there's no zeros. From our protip, we know if by the factorization there's no zeros on the diagonal, of U, that means all the columns of A are linearly independent. So what will be the number of linearly independent columns of A? Well, that simply means it's all the columns of A, so it's K equals whatever is the number of columns. So in this case, we call it M, right?
Oh, so K is just number of linear independent columns. Number of columns of A.
And so this will essentially be equal to our pro-tip, which is a question a lot of people have had in office hours. So I think it's worth mentioning that if you were to go from here to what the pro-tip is basically saying this is equal to the pro-tip. It's equal to using the pro-tip, which says all columns of A are linearly independent if the diagonal elements of U are not 0. Right? So this part we know from the pro-tip to be true. For if, let's say, there was a 0 element right here, right, and all these elements were like 1, 2, 3, so on, everything was okay. All of this is 0 because it's upper triangular, and then there's some elements here that we don't care about. We look at this last term on the diagonal and we say, okay, if I was to count the number of linearly independent columns here, and this is M, this is some N cross M. This is N cross M, M columns. So if I were to count the number of linearly independent columns in this case, I would say, okay, I see 1, 0, and there's no other problems. Everything else is fine. I can use this thing, which says if there's 1, 0 element, K is M minus 1. So everything other than this column is linearly independent. Right? And the last case is if you have more than 1 zeros, which is where I think most of the confusion is. So what happens if you have more than 1 0? You're looking at something like your U will be 1.0, 2.0, 3.0, some random numbers. Something here, 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 something here, and then 0.5, and then this is 0.0, 0.0, 0.0, 0.0, 1.0. Let's say this is, I'm going to call it 3.0. I'm going to call it, okay, 6.0. Let's make this 4.0. Let's make this 2.0. So this will be the last rule. You see there's 2 zeros on your diagonal. And then this says you have to look at the rows, which can be confusing. So what it's trying to say is that if the rows of U that have zeros on the diagonal are identically 0, so this is all 0 because it's upper triangular. I look at these last 2 rows, and I say if all the elements in these 2 rows are identically 0, means all of this is 0, these 2 are also 0, so this condition is satisfied. This is what it's saying. Then K equals the number of non-zero elements on the diagonal of U. So in this case, our K equals 3, which is M minus, what was the number of zeros on the diagonal? 2. Now, there might be cases when this will not be true. So you'll have something like this becomes, say, 1.0. And then you have to check for linear independence. Because it may just be the case, like in this, this one, you can tell that this is linearly independent, right? There's no way. This is all 0. None of the numbers here are 1, right? So there's no way I can find something here as a combination, right? So you have to look at combinations if you fail this test. So now we know how to count the number of columns, the number of linearly independent columns, right? We're good on that? Good. So now that we know how to do that, we're going to use that into solving for a system of equations. How do we do that? So we look at this and we go, okay, now that we've added, we call this AE, a new matrix, which is just all the columns of A with an added column B, and I'm going to check the number of linearly independent columns in A transpose A and AE transpose AE. Using LU factorization, I find my U and I find my UE, and then I look at the number of zeros. So let's try and do that for like some system of equations. And because this is, we'll just keep doing LU, and I don't want to do it by hand. We're going to do all of it in Julia, right? You can run it with me. You can do whatever you like with that. So I have a system of equations. It's 3 unknowns and 4 equations. So we already know it's probably going to be harder to find a solution because there's more constraints and there's fewer unknowns, right? So let's try and see that. So by magic, somehow, when you run this equation, when you run the first cell, it will give you this A that we have right here. My computer is just slow today, so it's going to take like a little bit of a time. It's pre-compiling a couple things. Yours might be running, yeah? Not yet. Yeah, it takes a while to pre-compile these things. Come on.
Why is it random? Yeah. Like the matrices, they're like the random function. I don't know what that means, right? The why is.
The matrices are in red. Oh, do you have a math error?
Oh, no. I was just wondering like how it's saying like A equals something, but then in the program it's like random.
Yeah, so I reversed and engineered it. I got the random matrices and I copied the solution into and I made the system of equations from that. So when you run it back, it gives you the same random value, and the way to do that is using the seed. So I set a seed to 10, so which is saying that it will sample from the same distribution every time. So I know that every time I call a random, it will give me the same matrix. But if I remove the seed, it's going to be random every time. But I want to fix it so that it's like reproducible. So what I do is I run the random, I make my A and B matrices, I copy them as homework problems, and then we use that. I don't want to write these down, so I will just copy them all the way. Well, let me reopen my Jupyter notebooks. I don't know why it shouldn't be this slow. It's just weird. Otherwise, we'll go to Illumitask. That's so weird. So weird.
And, okay, so this isn't directly related, but when we run like the LU like function in Julia, the answer is like both an L matrix and a U matrix. Okay.
It'll return like a tuple or like a structure of it, and you want to access, if you want to access the L, so let's say you save it in LU of A, then you can get LU of A dot L by, and then that gives you the L. And there's another way to do it. We'll look into it. I think that's a good question. Open it. Oh, it ran. Thank God. Okay, so we got the A matrix right here, which is the same as the one we have in the question. Then we run this and we get a B matrix. Next thing, if we're checking for existence, what you do is you build that augmented matrix. So I put A, and then I add B as a column of A. So we can see what this looks like. We can say display AE, and I'm going to split that cell. So it's basically the A matrix, all of its columns, and then the last column is B. So we have AE. Now what you want to do is you want to get this formulation. So I need the P, LU, PE, LE, and UE. What I do is I do LU decomposition of A transpose A and AE transpose AE. And I save it as these variables. I'm going to split the cell again so that we can see what you were talking about. And when I say display LUA.P and display LUA.L and then display LUA.U. So you can see all of those matrices, and the dot operator you can use to extract them. That's one way to do it. It'll give you what you want. Another way to do it is simply what you'll see in your homework. So P, L, U is equal to LU decomposition of A transpose times A. So let's see. Now I can try to similarly display P, display U, display L. should have given the same thing. L is correct. Oh no, L is U. So this is U. This, and then I think you need. Wait. This is probably it. U is correct, and then L is weird. What? Okay, so display.
Have just like a quick refresher on like what the P matrix like is. Makes any sense?
Go for it. So what the P matrix is doing, in this case, we say that our P is simply the identity matrix. So then here it's not doing a permutation. But then when we looked at our homework, like this one, and we had a P matrix, in this case, so if I try and multiply, we were trying to do PA is equal to LU, right? And then this is homework 4, right? Problem 2. So P matrix, essentially what it does is, it's called a permutation matrix. And it permutates the different rows of whichever matrix you multiply it with. So when I say P times B, it will do, if you try and multiply it out, it will be 0, 1, 0, 0, 0, 1, 1, 0, 0 times B, which is 3, 6, 9. And you'll see that, and then to do it like without doing the multiplication, if you were to predict it, you will compare it with the identity matrix. So the identity matrix is just 1, 0, 0, 0, 1, 0, 0, 0, 1. From this, if you compare it with our P matrix, you say that, well, from the identity, I can say that the first column, first row of the P matrix is the same as the second row of the identity matrix. The second row is the same as the third row, and the third row is the same as the first row. So when I multiply it to anything, this map should follow. So when I multiply it with B, you'll see 0 times 3 plus 1 times 6 plus 0 times 9. This becomes 0 times 3 plus 0 times 6 plus 1 times 9. This is 1 times 3 plus 0 times 6 plus 0 times 9. You add it out. This is 6, 9, 3. So this map holds true. The first number becomes the second number between these two. Second number becomes the third. The second number comes from the third number. So this comes from this, and the third number comes from the first number, right? So basically, yeah, it does this kind of a mapping, but it's easy to see why it does that when you compare it with the identity matrix and you see what it's doing, right? Why we do it is going to be essentially is to say that we'll come to it in the end, and it'll be clear why we need it at times. But the idea is that that's what it does, and this is how you can get it. Then when you get it from Julia, what you want to do is finally to check, we want to check the diagonal elements of U, right? So the way to do that is to do this. And this gives you the diagonal elements of U. So this was our U right here. These are the diagonal elements. It's 20, 32, 11 point something. And we note that none of those are 0, right? So what is the number of linearly independent columns for this A matrix? A has 4 rows and 3 columns. So our M is the number of columns. Yes.
No zeros on there.
Exactly. So we know the K is 3 for this, for U. So the number of linearly independent columns in U is 3, right? Now I want to find the number of linearly independent columns in AE. So we did the LU factorization of this thing, and we looked at the diagonal elements of the U matrix. And when we look at it, there's no zeros, right? So in this case, what do you think the number of linearly independent columns is in UE? Yep, because we added a column, right? So now we know that it does not have the same number of linearly independent columns. 4 is not equal to 3, right? So we can say that the solution does not exist. That's it. AX equals B. That was our objective. That's how we started all this. I know it can be round and around. It takes a couple turns, but that's our objective. That's what we're trying to do. So we're good? Do you want to look at one more example? Yeah? So let's try the other one, which is a slightly bigger matrix. So this one is a 5 cross 5A, and x values, I haven't written them down, but the x vector is also x1 to x5. There's 5 unknowns and 5 equations. So my x is x1 to x5. And I don't know these, right? I'm trying to find these. Or I'm trying to find if they exist. So we do the same thing. We get the A matrix. And we get AE by concatenating the B vector. Then we get the LU decomposition of A transpose A and of AE transpose AE. And then finally, you look at the U matrix you got from those decompositions. So let's see what our U matrices are. Getting an error? What does it say?
It's a singular exception.
Run it again. Do you have the random seed there? Yeah? The random dot seed is 10. Yeah? Okay. Try running it again. Still? It may be because of the random values. Maybe you want to run from the top, although I doubt that would be the case, but just do it once. Which cell does that? Is it this one?
Yes.
Do you want to display your A and your B matrices to make sure they're the same?
Oh, it's saying B is not defined.
B is not defined. Do you want to copy this statement? Is the B equals to this in the code?
No, it's just saying not defined. Oh, okay. Okay, yeah.
Yeah.
But then the next cell is running out.
Check your A and B. Are they correct? Do they look like the vectors that you need? Like their value should be exactly the same as the thing. They are. And then in your LU decomposition, you do A transpose A and AE transpose times AE. That's weird because this will run. Do you want to check? So if it gives you singular, if it gives you that singular exception, it's usually sometimes that it's trying to divide by 0 when it's trying to find the LU decomposition. So what you want to do is, it usually doesn't happen because it shouldn't happen in this problem, and it's weird that it's happening for you, but do you think I should? I'll check it in the end. I'll look at your solution because it should be the same. Yeah. But maybe you can just see what I have up there. And then this one just says, I don't know, can you see it?
Yeah.
Does that help? Okay, we're good. So then we did the same thing. We got the LU decomposition of A transpose A and AE transpose AE. We looked at the U matrix, and there's no zeros here. So A has 5 independent columns. And AE, well, it looks like it has 6 independent columns, but we look at this last number, and it is to the power of minus 15. So that's approximately 0, right? So we're going to say the number of linearly independent columns from the second rule of semi-pro-tip, we can say it's k is equal to m minus 1, which in this case is 5. So here, when we're reporting it, we'll say it's 5 and 5. And then our comment about its existence will be that the solution does exist. We'll do the same thing for a matrix of the size with 50 equations and 30 unknowns. And there's no way we're going to want to do it by hand. So we'll just look at this. Now, this is like, I think this is a problem in your homework where you do like 50 equations and 30 unknowns. And the problem with that is you want to look at the diagonal elements, but there's like 30 diagonal elements, right? So it's a little hard to see. So what you'd want to look at then is maybe what we can do is we can look at, instead of looking at all of the diagonal elements, we'll just look at whatever is the minimum absolute value, right? So we'll do a minimum of absolute value of all the terms in this diagonal matrix. And similarly, we'll do a minimum of the absolute value. And we need the dot operator because we want the absolute value of each element, right? And that's a bracket issue. Maybe one more. Did I not add one more? Yep. Okay. When I run that, I get no zeros, right? If there was a zero, then that should have been the minimum value. But since the minimum value, absolute minimum value in there is 133, we can say that neither of these LU decompositions have a zero on their diagonal. So from here, the number of linearly independent columns in A are then 30. And the number of linearly independent columns in UE are 31. The one extra from the B. And we say that the solution does not exist again. So we see that there's a way that we can scale this method. We can probably write a function that can just get a system of equations and tell you if the solution exists, which should come in handy, right? So now we've convinced ourselves that we like this method and that we don't want to be doing alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 is equal to b and then try and find out the solutions. It's not scalable. So once we know that our system exists, that a solution for our system of equations exists, we said that it could either be an infinite number of solutions or it could be a unique solution. So we should have an extra condition to be able to see, to be able to talk about the uniqueness of solution. So what we do is we can say that the system of equations Ax equals b has a unique solution if b is a linear combination of A, which was our condition for existence, right? So we already know how to check for that. And then the extra condition is that we want to check that the columns of A are all linearly independent. Now, do we know how to do that? Yes, we do. We can use the pro tip, which says that the columns of A are linearly independent if the following are true. Either A transpose A, the determinant is not zero, or from our LU factorization, U has no zero elements on its diagonal, which was essentially the first point of our semi-protip, which forms the full protip. So we're going to use this definition, and we're going to try to find a solution for the system of equations with, I think this is 5 unknowns and 6 unknowns and 5 equations. Oh, this one's right here. I will push these down. Meeting has ended. What? Why? So this one, this is actually here, like what's written here is actually here. I'll push it in the final, I'll correct it. But let's say our system of equations is indeed with 5 equations and 5 unknowns. So let's say this was my A and B. Not that one. And this is the same as from our previous problem, this one, this right here. We got it all the way down here. It's the same system of equations. We look at the same thing that we did before, but this time we're going to observe the uniqueness as well. So we did the exact same method, and the beauty of this analysis is that we don't have to do anything new after checking for existence, because we just note here that when I look at the U that I got from the LU decomposition of A transpose A, it has no zeros in its diagonal. So that means empirically, using the protip, the columns of A are linearly independent using this formulation. So I know that the system of equations, first we checked its existence in the previous part, and now we've talked about the solution being unique, right? So we can comment and say that solution does exist, and we also know that the solution is unique. Great. Let's also look at a system of equations where I know there isn't a solution. So we'll look at this big system of equations, and I'm going to bring it down right here. And when I run my A and B, let's just see A, it should be exactly the same. And it is. So this is my A, and the B is also the same if you want to check. And then we do the same analysis, and we got an LU decomposition. And here we will note that A in itself, the number of linearly independent columns in A is 5. And we're not sure about what to do with the second one, which is the UE matrix, because it has 2 zeros, the 2 in the end, right? So what we'll have to do is we'll have to look at the full matrix. So I look at the full matrix, and I see that indeed the last 2 diagonal elements are 0, but the rule was, so if I look at all the rows that have the 0, if they're all 0, if they're completely 0, that means k is equal to the number of columns that have non-zero elements. So in this case, k is equal to 5. And from here also k, oh wait, is it 5? Yeah, that's 5. And from here also I get k is equal to 5. So I will say that the system of equations, it does have a solution. Are we lost? Yeah. So we talked about, for checking existence, we're good till here. We want to look at the U matrix after the LU decomposition, right? So here I get these 5 elements, and this is essentially 0 for the A matrix. And then here, again, I have 5 terms, and these last 2 terms are 0. So if we're using our semi-pro tip for this one, when there's 1, 0, k is equal to m minus 1, right? So here, m being 1, your k equals 5 for this formulation. For this one, I see, okay, there's 2 zeros. So what did the tip say? The tip said that you have to look at the rows that have the zeros. And if all of the elements in those rows are 0, then k is equal to m minus whatever the number of zeros were. So I look at my U matrix, and I see, okay, the last 2 elements where the diagonal was, both of them are zeros, right? The whole row is 0. So I can say that k equals m minus 2. So in both cases, k equals 5.
And that means that the solution is
Yes, exactly. We say that the solution exists, but is it unique?
No, it is not. It doesn't determine it.
Exactly. Because we looked here when we were checking the number of linearly independent columns in A. With the LU decomposition, we found a 0 in the end. So from our pro tip, if we find a 0, we say all columns of A are not linearly independent. Right? So that means that the solution is not unique. Okay, so now that we've covered existence and uniqueness, we want to move on to least squares, right? So chapter 8 of our booklet, we look at, so let's say we're given a system of equations, ax equals b. We see that there are 4 equations and 3 unknowns, and a lot of the times, when we look at it graphically, what we're trying to do is we have 4 lines, so like 4 equations means 4 lines, and we're trying to find an intersection with 4 lines. And a lot of the time, in a 3D world. So a lot of the times, it's hard to find a solution when there's more equations and fewer number of unknowns. So what we want to do is we want to find the best approximate fit. So let's see, for this system of equations, ax equals b, does a solution exist? Well, we look at the LU decomposition, and we look at, okay, A has 3 linearly independent columns, and AE has 4 linearly independent columns. They're not the same. So, well, the solution does not exist. So now we know that there is not an exact solution to our problem. So we'll have to find what is an approximate solution to our problem, right? Do we know how to do that? Well, let's see. We have, I don't want to mess this up, so let me look at my solution. Yeah, so we'll define, from our system of equations, we have, we have A, nope, yes, nope, okay, come on. We have AX equals B, and I say A transpose A times X equals A transpose B. Can I do that? I don't know. Let's see. So the reason for us to do it is that I want a square matrix here. And what I will do is I will do an LU decomposition of this. So I'll have an LU decomposition, and I'll try to solve for X. So the way for us to do that is by using, I will define a new, I'll call it a new B. So let's say this is C. Let's call it Z. Right? So I'm going to define my Z to be A transpose times B, right? So for my system of equations that is given like this, it is A transpose A times X equals C. what I will do is I will do a forward substitution. I will first find my LU decomposition. So LU of A is equal to LU decomposition of A transpose times A. Because what is my new A? My new A is this term right here, A transpose times A. So that's what the LU decomposition should give me. I use that and I say how we normally solve with LU decomposition. I say I find a Y, which is the forward substitution of my L matrix, and my B, which is now Z matrix, and an X star, which is the backward substitution of my LU, the U matrix, and whatever I get from Y, which is our normal way of solving for LU decomposition, right? We get UX equals Y, we find Y equals L times Y equals B. So that's what we did there. And I did not run this function, so it gave me a value of my X, right? So it seems we found a solution. So let's see, if we found a solution, what should we find? We should find that A transpose A times X star, it should be equal to B, right? Or Z, and display C for a system of equations. They're equal, because that's the solution we found, right? From our system of equations? No, not good. From here, I found A star. So I compared the left-hand side, and my left-hand side is A transpose times A times X star. This is a star right here. Yes. So A transpose times A times X star, and here is my Z, which we define to be A transpose times B. I display both sides, and I see they're comparable, right? So we're good. We found the solution. But was this the solution that we were trying to find? Not really, right? We were trying to find solutions for approximate solutions for AX equals B. We checked that the solution actually does not exist, but what we did was we pre-multiplied by A transpose, we did the whole calculation, we found a solution for the system of the modified system of equations, which was A transpose times A transpose A times X star equals A transpose B. Now, does that mean that is also the solution for A times X star and display B? Does it also solve this system of equation? It doesn't, right? And it wouldn't, because it was supposed to be an approximate solution. It wasn't an exact solution, right? It solves this system of equations, but it's not the same as solving this system of equations. So we might think, well, I guess we made a mistake in solving our system of equations. How did that happen? Well, this is optional reading, and you don't need to know this. This is completely my way of saying this, but if you look at the LU decomposition of A transpose, which will be, so when we did LU decomposition of A, we looked at LU decomposition of A transpose times A, right? So if I'm trying to do it for A transpose, the transpose of A transpose will be A. Does that make sense? Yeah. And then I multiply it with my A, which is now A transpose. And I look at that LU decomposition, and well, that's what what we thought we were doing wrong, we found, well, A transpose isn't actually linearly independent. Same thing? Okay. So we know that it's an approximate solution, and you can't just say, I'm going to do A transpose on both sides, and still expect it to be equal. It's not equal. It's an approximate equal. So what we do is we want to quantify the error that we just found from our x star. And the way to do that is I'm going to define my error vector, E star, to be equal to A times x star minus B. And I look at that, and it's a pretty significant error, right? It's an approximation, so there should be an error. And from our definition of norms, we know that we can find the norm square error by taking the square root of the sum of the square of all the elements of E star, right? So this should give me the normed square error. Let's see what the norm square error is. The norm square error is 5. Now, this tells us so let's see how this is actually even correct. This will probably be helpful. So x star, we know that, let me write it down even. We know that x star is the exact solution for A transpose times A transpose A x star equals A transpose B. So the norm square error should be 0. Let's check. I'll update these solutions, by the way. I'm like, okay, if you want to stay with it, but so I get E exact equals A transpose times A times x star minus A transpose times B. And then I'm just going to copy this, paste it here, and call it E exact. And let's see what our normed error is. As we expected, the normed error is 0, because x star is an exact solution of that problem, right? So we've now found a way to approximate our solutions. I know that this x star will give you the least normed error for this system of equations as well. How do we know that? Well, we've proved it mathematically, and it's in our booklet, but that proof is optional. And if you decide to go over it and you have problems with it, reach out in office hours, right? It's not, if you can just take our word for it, we can tell you that the x star that you found from solving this system of equations does give you the least error. So it's the best approximation according to this normed space. So now that we have that behind us, now that we know how to find approximate solutions, we can use that for one interesting application. And that interesting application is line fitting. So we are able to fit lines to assist to data that we've collected. So we collect data in, like, when you're doing chemistry examples and whatnot, and you have a bunch of data that you're trying to fit a line into, and that's where we can use this. So let's say we redefine our system of equations. So we've been using AX equals B. instead of using ax equals b, instead of b here, I'm going to start writing y. And instead of so this was ax equals b. This was ax equals b. And we've changed that into b equals y equals b alpha. It's the same thing though. So let's say I have a couple data points where my x and y are these. So let me split this so that we can see what our data is. So let's say you collected data where x was these many points and y was these many points. So my x was 1, 2, 4, 5, 7, and my y was 4, 8, 10, 12, 18, just some random numbers. I plot these points on the scatter plot, and I see my plot, which will take, I don't know why my computer is so slow today. But let me start writing down stuff in case. Yep. Okay. So we see these points, and what we want to do is we want to fit a line across these points. How do we do that? Well, we will take the shortcut out in the interest of time, times b times v times y. From here, from our ax equals b, I know that y is this phi times alpha. I know I have my x vector and I have my y vector, and I'm trying to find the alpha, the m and the b. So what is alpha equal to? Well, when we were doing ax equals b, we did the transpose, right? Transpose on both sides. We multiplied with it. So I'll do the same thing here. I have y equals phi times alpha. I'm going to multiply both sides by phi, and I say phi transpose y equals phi transpose phi times alpha. Does this look like A transpose A times X, right? So from here, I'm going to make an assumption that this is invertible, which is saying that a solution exists to the system of equations, right? Which also means that the determinant of this thing is 0. I'm going to assume from my data points that that's true. And I can say alpha is phi transpose phi inverse phi transpose y. And that should be my alpha star. I don't know why that happened. But yep, that's that. So we're going to use that formulation. And, okay, go away. No, go away. Let's just stop this application. Damn. This goes away. When all else fails, there's Task Manager. Pen. Oh, God damn it. Okay, great. Okay. We're back. So from here, I'm going to use that formulation, and I get my alpha star is inverse of phi transpose times phi into phi transpose times y. I run it, and I will get a system of equations. From there, I'm going to start writing y hat is E times alpha star. And on the same plot, I'm going to plot my x and y hat. So we know the alpha star, which is basically our m and b. So we found the slope. We found the slope of our lines, and we found the intercept, the m and b. From here, I can tell that my m is 2.3 and my b is 2.1 something. I use that, and I plot my y hat, which is the estimate, which is my line estimate, which is phi times alpha star. I plot those together, and this is the line fit that you get. Right? So now we know how to fit a line to a bunch of points. Another interesting example we can do is I want to fit, so let's say x goes from minus pi to pi in the intervals of 1, and I get y is sine of x. So I get a bunch of these points. And what I want to do is I want to fit a system of equations here. So I will define a phi. I'll have this. I think we're running out of time, so I'll just look at the answer solution. And we'll look at the code and we'll discuss it in the interest of time. Yep, let's just go all the way back there. So we were here, polynomial fitting. Yep. So let's just say using plots. Basically, oh, I already have it up there. So what it does is, I'm going to define the phi. We had these system of points, right? Then I defined a phi, which was a 3-degree polynomial in my x, and I found the alpha star exactly the same as this thing, but because this time it was a 3-degree polynomial, it looks something of a bigger matrix. It'll be like it's 1, x1, x1 square, x2 square, x3, x1 square, x1 cube, x1 to the power 4, and so on. We can see the phi matrix if you like. And from there, you get the alpha star from the same code. I define an x hat just to get a smoother curve from minus pi to pi. If this runs, I'll show it, but if I was to just plot it, it'll just give me a fit through these lines. You want a more detailed plot, right? So you want your x to go from minus pi to pi, and instead of going in intervals of 1, I want it to go in intervals of 0.1. And then there, I predict my y hat, which is phi hat times alpha star. I plot it, and voila, I have an approximate fit of what is a sine function using just a 3-degree polynomial. So it is 1 plus c1 times x plus c2 times x squared plus c3 times x cubed. Oh, it runs. Amazing. So we have this. I define my phi to be this. With unknown weights, and we're trying to find out the weight matrix of phi. Yep. So these are the different coefficients. So if I was to write down what I found, like what is my approximation, I will say that, well, my approximation is simply that y, if it'll let me write, I can say, if you would just look at this and bear with me, it says y is 0.012 plus this 0.84 times x minus this almost zero term times x squared